right. Okay. Thank you all for joining us for tonight's 12 Things That Make Life on Earth Possible with our host, Michelle Nichols. Now, Michelle is my favorite astroeducator. I love having her come and do Zooms at the library. But in her daytime, she works at the Adler Planetarium. And I know we recently went through a partial eclipse that unfortunately the weather got in the way. But there is another eclipse coming up in April. And if you didn't get a chance to get some glasses, the library still has a bunch of glasses. So as it gets closer to April, come back to the library and get some glasses for you and your family. We were reserving them originally just for Bloomingdale residents, but we have so many left over that anyone's welcome to come and get some glasses. So mark your calendars for April, everybody. Okay, now I would love to get started and introduce our speaker tonight, Michelle Nichols. Hi, Michelle.
Hello, Christina. Thanks for having me. All right, ready to go? All
Yeah, we're
right,
ready to go. Oh, and
let's get going.
anybody ask questions in the chat or Q&A, and we'll get to those at the end, please.
Absolutely. Yeah, you can put them in either one. We'll find them. So excellent. Hi, everyone. My name is Michelle Nichols. I'm the Director of Public Observing at the Adler Planetarium. And so in my day job, what I do is I'm in charge of all the Adler's telescope and sky observing programs and events. And at night, in my spare time, I love to give talks at libraries, and I've been doing this for many, many years. This talk I started doing maybe about a year or so ago, a couple years ago, something like that. And it was based on an article that I read in National Geographic from a few years ago. And it was titled something like 12 things or 13 things or something of that nature, of those things that make life on Earth possible. And I thought that would be an interesting talk. And so what I've done is I've taken some of the information that was in that article, but I've added in a few more astronomy connections than what we've got, than what was in there. Mainly, I wanted to show you some examples of other places in the solar system that, hey, here's an Earth thing that might make life on Earth possible. Where do you find this elsewhere? Where do you not find this elsewhere? So that's definitely a twist on the topic that I thought you might think pretty interesting. What's also fascinating is this list is, number one, not necessarily comprehensive. There could be other things that you could very much argue that should be on the list that aren't. Also, I've got all these 12 things in a particular order, but that was just so I could tell a better talk. You could definitely make the case of putting different one of the items on the list in a different order in terms of priority, or which one is absolutely the thing that's the reason we're here and what's next. And so I didn't put them in order of importance. And then the other thing that I find fascinating to think about is we have yet to find life anywhere else in the universe. We don't know if these particular 12 things that I'm going to talk about are the case for every place else. Do we need all the 12 things I'm going to talk about? Could you not have one or more of them and still have life exist? We won't know until we find some other life elsewhere. And it's something that we could argue about for days. But until we find an example of life someplace else in the universe, we don't know the full range of places that might be hospitable to life. So, with that, I'm going to show you at least what seems to make life possible here. Whether this applies to every place else, to be determined. So, let's get going. All right. I'm gonna wait till it shows up and it's loading, and there we go. All right. Okay, what I'd like you to do is take a look at our planet. What do you see? You're probably seeing different colors, different shapes. You see blue, you see brown, you see green. The green is a significant sign. That is the unmistakable sign of life on this planet. What does Earth have that makes it possible for life to be here? It's a really interesting question, as I said, with probably many more than 12 possible answers. Now, as I mentioned, I've numbered these items, but they're not in a priority order or an importance order. Just the order that made sense to me when I wanted to put them together for a cohesive presentation. So why don't we get started? The one that's first on the list, you probably didn't think of, and that's carbon. Now, in order to talk about carbon, I need to take us back a few steps, back to probably some chemistry that if you're an adult like me, you probably haven't thought about some aspects of chemistry since the last time you took chemistry, which might have been high school, middle school, maybe. So life on Earth, specifically on Earth, would not be possible without the element called carbon. Now, carbon is the fourth most common element in the entire Milky Way galaxy. Now, what's first? Hydrogen. Second, helium. And third is oxygen. Carbon is fourth. Here on Earth, carbon is part of molecules like DNA. DNA basically is the blueprint for life on Earth. Our DNA determines what kind of life forms we are. Life on Earth, meaning the molecules that life is made of, is based on carbon. Now, could life exist someplace else based on some other element? Well, maybe. This is possibly something you haven't thought about since the last time you took chemistry. This is the periodic table. This shows us the naturally occurring elements in the universe. So you break different materials down to their most basic common denominator, and you get atoms. And individual atoms contain protons and neutrons and electrons in different numbered amounts. And those different numbered amounts we call elements. And the periodic table is actually not randomly distributed. This is not the order in which the elements were discovered. This is based on how many protons they've got, but also the columns in the periodic table show you elements that have very similar characteristics. We'll come back to that in a second. In terms of whether life could exist elsewhere, well, scientists look for what's most probable. What's most abundant? And then how elements act chemically together. So life elsewhere is probably not based on materials that are rare, such as the two that I've got highlighted here. IR stands for iridium, PT stands for platinum. So could you have life based on those elements? Maybe, but it's unlikely because those two particular ones, you don't find a lot of them, a lot of either one elsewhere or here. So having life based on something very rare is very unlikely. Now, the 10 most abundant elements in the entire observable universe are hydrogen, helium, oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur. It could be possible to find life that doesn't use this set, but at least on Earth, we haven't yet found life that isn't based on some subset of this set, because this is the most abundant stuff that you find in the entire universe. What is most probable? Life might be based on the most abundant stuff. Now, why carbon here and not something like what's right below it on the periodic table, silicon? Now, again, when you look at the periodic table, atoms that have similar characteristics are in the same column. Carbon and silicon are chemically very similar. Both types of atoms can form bonds with up to 4 other atoms simultaneously. So what do you get when you combine carbon and 4 other atoms, or silicon and 4 other atoms. Well, on Earth, lots of rocks contain silicon, and there's actually more silicon than carbon in our crust. Quartz is an example. That's the mineral on the left. Quartz is an example of a mineral that contains silicon. Granite is the rock on the right. That's an example of a rock that contains minerals that contain silicon. Now, land plants get silicon from the soil, and the silicon is used by those plants in building the plant's tissues. In the ocean, phytoplankton consume enormous amounts of silicon. And where do they get that from in the water? Well, the land, rocks, and everything are worn away by water. All that silicon goes into the rivers and streams and flows out into the ocean. So the rivers and the streams erode the rocks, and that eroded material flows out, and then it is consumed by phytoplankton. Silicon is absolutely an important element here. Where carbon and silicon differ is that here on Earth, chemical reactions involving silicon are much slower than reactions involving carbon. Molecules based on silicon and hydrogen are also not very stable in the presence of water. At our temperature and our air pressure, carbon plus oxygen, carbon dioxide, is a gas. This is a waste product. It makes it easy as a gas to get rid of carbon dioxide as a waste product. At Earth's temperature and pressure, silicon dioxide is a solid, like quartz. So getting rid of it as a waste product is a lot harder to do. It doesn't mean that life can't be based on silicon elsewhere if the temperature and air pressure is different. But at least here, it's much easier for life's complex reactions to be based on carbon. It's easier for us to get rid of a waste product. It's easier for the chemical reactions to occur. But if your temperature and pressure are different someplace else, maybe it would be easier at that point for silicon to be the main element that's used. So interesting to think about based on the temperature and pressure that we have here on our planet. Number 2, we have an ozone layer. Sometimes hard to think about at the end of October, but maybe you think about the ozone layer in the middle of summer. Well, why do we do that? Well, I'll get to that in a second. Now, the oxygen you breathe is a molecule. This molecule is made of 2 atoms of hydrogen that are stuck together to form one molecule. Ozone is 3 atoms of oxygen bonded together to form one molecule. Where ozone came from originally, it wasn't here when our planet first formed, when we first got an atmosphere. Our atmosphere initially did not contain ozone. Where it came from was plant-like organisms in the Earth's ancient oceans added oxygen to our air. So they gave off oxygen. The oxygen bubbled up out of the water and was added to the atmosphere. Then interactions between that oxygen and ultraviolet light from the sun created over time a thicker and thicker high altitude layer of ozone. And as this layer got more and more dense, this ozone shielded early land species from lethal radiation from space. So what are we talking about here? We're mostly talking about ultraviolet light. Now, this layer still protects us today. And this ozone layer keeps out most of the ultraviolet light that comes from our sun. Now, we put this ultraviolet light in different ranges of energy. The range of energy that you may have heard of called UVA, so ultraviolet A. This range of energy is less energetic. This is the range of light that gives you a suntan. All right. A little bit higher energy, a little bit more destructive is UVB. This is the range of energy of light that gives you a sunburn. The range of energy of light called UVC, which you may not ever think of because our ozone layer 100% blocks it. This is the range that can actually start to do damage to your DNA, which is based on carbon. So without the ozone layer, this high energy UVC radiation would cause our DNA to mutate. and life on land and in shallow regions of the water, it would be very hard for complex life to develop and evolve. So we absolutely needed an ozone layer thanks to this ultraviolet energy that comes from the sun. It's not that you can't still get damage from UVA or UVB, don't get me wrong, but it's UVC that it's really, really good that that does not reach the ground here on Earth. So it's also interesting, you send astronauts up into space. We need to make sure that our spacecraft are shielded from this harmful radiation from the sun because you're up above the ozone layer at that point and you don't have that layer of protection. Where else do we not have an ozone layer? Well, planet Mercury, so over there on the left-hand side, no atmosphere, no ozone layer, no protection from anything from space. Mars, the one on the right, has a very thin atmosphere, no ozone layer, very little protection from radiation from space. This is something future Mars explorers will need to contend with. It's not enough to have an atmosphere as protection from radiation. That ozone layer here on Earth is our protection, and so that's definitely something that we need to be aware of, because if you go to Mars, your spacecraft will have to protect you, your spacesuit will have to protect you, your buildings, your constructed places, those will have to protect you as well. What's next? Take a look at our planet right there. So second from the right. Take a look at our planet. We're seeing the continent of Africa right here, a little bit of the Middle East here. We've got an island right there, Madagascar. So we have a really interesting planet. It has a moving surface. You don't really think about it when you just take a look at a picture of our planet, but our planet has a surface that is split into several large plates. In northern Illinois, we are on the North American plate. So this is the North American plate right here. So inside this yellow line, this is the North American plate. There are many others. So you've got the European plate, the North American plate. Where these yellow lines are boundaries between the plates. And these plates move. They move anywhere from 1 to 4 inches a year, or about the rate your fingernails grow, maybe slightly faster. Over millions of years, these plates sometimes collide. So where you see any of these arrows, where the arrows are coming together, you've got two plates colliding. All right. The Indian plate coming up against the Eurasian plate. You've got the plates coming together, and what gets pushed up? The Himalayan mountain range. Plates move apart. So wherever you've got the arrows moving apart, you've got plates moving apart, as they are doing in the middle of the Atlantic Ocean. This causes Europe and Africa and North America to ever so slightly move farther apart. So every year, our plane rides from North America to Europe get, maybe about an inch farther apart. It's not much. But plates also slip past each other. The Pacific plate and the North American plate slip one past the other. California is the obvious boundary. Now, you've probably heard the side joke, oh yeah, LA get the big enough earthquake, it's going to slide right into the ocean. That's not true. That will not happen. But what is happening is Los Angeles and San Francisco are very slowly getting closer to each other. So in some number of tens of millions of years, Los Angeles will be a suburb of San Francisco. So it's interesting to see where you've got these plates slipping past each other. You sometimes can see this visually. Here's an example. This is the example of one plate moving alongside another one. This image is showing the movement of the Arabian plate against the African plate. And where the boundary is right here is literally this fence line or this wall. And so you are seeing this wall getting pulled apart because one plate is moving against the other one. Fascinating to see that, because you've got this wall built directly on top of one of these fault lines. There's another type of movement, one plate can dive below the edge of another. And where you've got this orange indicator with the teal colored lines, this is where this is happening on the planet. And this kind of one plate diving below the other one creates deep trenches in the ocean. These areas on our planet are responsible for the world's biggest earthquakes, the most terrible tsunamis, some of the worst volcanic eruptions. Now, Earth's surface is slowly in motion. Now, why is this motion important? Well, this motion cycles carbon through the air, the land, and the sea. So where don't we see this in the solar system? Well, as far as we can tell, Mars and Venus have surfaces that previously, long time ago, crumpled and deformed. It is very likely that Venus still has active volcanoes. There's some scientific evidence that came out not too long ago that seems to show Venus with at least one active volcano on its surface. But neither planet has a surface made of large moving plates. It's interesting to see that both of these planets have atmospheres, but there are no moving plates here. No life on these two planets as far as we know. We don't see any evidence for moving plates in either one. So, could this be extremely important? Well, at least for the cycling of carbon through the entire planet, yes. You could absolutely argue that liquid water might be the first thing on the list. I needed it as number 4 to tell a good tale. But you probably could say without water, life on this planet would not be possible. The blue in this picture, liquid water. Liquid water on our planet is significant. Now, I'm not saying the same thing twice when I say liquid water. I know what you're thinking. You're thinking, wait, liquid water, that's the liquid, right? No, not exactly. Water is a molecule. It's made of 2 atoms of hydrogen and 1 atom of oxygen, H2O, right? Water is what we call a polar molecule. It has positive and negative ends. Now, what this polarity does is it means that water can dissolve and mix into other polar molecules like DNA, like proteins, like amino acids. Water allows cells to use these materials effectively and helps juice up those chemical reactions. Water allows the complex chemical reactions of life on this planet to occur. Water helps things move. Water carries nutrients into various cells. Water carries waste away, like carbon dioxide, right? On Earth, water is critical for life, and life is based on the availability of water. And I just said water carries away carbon dioxide. If it's a waste product in the liquid water, that is, of course, you breathe out carbon dioxide as a gas. But that goes into my next point, which is I wasn't misspeaking when I was saying liquid water. Water is just H2O. What form of water is it? What is the state of matter that we're talking about? I just mentioned carbon dioxide as a gas. Well, you can have water as a gas. That's water vapor. That's the stuff that comes out of your tea kettle. Liquid water, that's the stuff that comes out of your water faucet. Solid water, that's ice. That's the stuff that's in your freezer. All right. We find all this all around our solar system. Ice, liquid water, water vapor. When we look for water in our solar system, we are in part looking for the places where life could exist. Scientists studying our solar system are often in a search for water. Now, why is water common here? Water should be common in the entire universe. And this comes from knowing what stars are made of. Wait a minute, you're just talking about water. Now you're talking about hot Basel gas, stars. What are we talking about here? Scientists in the 1800s figured out how to split the light from a star into its component colors. You know these colors as the rainbow. Embedded within the rainbow is a pattern of dark lines that correspond to what the sun is made of. All right, so here we've got some individual elements and the individual patterns of lines that make up the fingerprints that we see of those particular elements. And here at the bottom, we've got a rainbow with all the dark lines from our sun. What you want to do is you want to take all the fingerprints from all the different elements and molecules and things that we know about, match them up to what you see in the bottom row there, start to pick out, oh, here's the hydrogen pattern, here's the helium pattern, here's all these patterns. Can we find all the stuff that we know about in the sun? And we look for these characteristic patterns, right? Elements were identified by these characteristic light patterns, and by the early to mid 20th century, thanks to astronomer Cecilia Payne, astronomers understood that thanks to the patterns that we see in the light from stars, that stars are mostly made of hydrogen. Helium is a distant second, and then there's a smattering of other stuff. Okay. Now I mentioned the most common elements are hydrogen, helium, oxygen, carbon, and nitrogen. Helium doesn't really combine with anything. Thus, the most common compounds in planets turn out to be hydrogen, oxygen, carbon, nitrogen, hydrogen and oxygen, water, hydrogen and carbon, methane, hydrogen and nitrogen, ammonia. Interesting. So, water results from hydrogen reacting with oxygen. And I mentioned methane results from hydrogen reacting with carbon. Here we've got ammonia. So far from the sun, all this stuff that I just showed you freezes as ice. The easiest of these to freeze is water. On Earth, we can have gas form of water, liquid form of water, and frozen water. At Earth's temperatures, though, methane and ammonia are still gases. Where it's a lot colder in our solar system, you can have water ice, ammonia ice, methane ice, and others. So we've got this stuff that can all, we've got nitrogen and carbon and nitrogen, carbon, and hydrogen that can all react with, sorry, nitrogen, carbon, and oxygen that can all react with hydrogen. But the most abundant stuff, the easiest to get out of all these reactions is water. So where did the water come from? All right, why is it here at all? Well, first, it came from volcanoes. As Earth and Venus and Mars and Mercury evolved, they released gases from their middles through volcanic eruptions. Now, we see evidence of volcanoes on all the rocky planets. We don't see any active volcanoes on Mercury. We don't see any active volcanoes on Mars. We probably see active volcanoes on Venus and definitely on Earth. Volcanoes on Earth continue to release these gases today, and this produces a lot of water vapor. On the early planets, these gases formed the early planet atmospheres, and some of the water vapor condensed onto our surface. All right, so we have all these various compounds all over the place, far from our surface, far from our Earth. That's when you can get the ammonia, and you can get the ammonia and, gosh, I'm blanking, the ammonia and the methane forming ices. But here on Earth, we have the right temperature and pressure. We get water vapor, liquid water, and ice all at the same time. We don't have that with the other materials. So that's why water is very, very common. H2O is very, very common here. So we've got the water coming from volcanoes. Next, some water came from comets. Comets contain water ice and other types of ices. Here we've got 3 comets right here. You have to trust me that there's ice here. They look like snowy dirt balls. Comet impacts may have brought water ice to the surfaces of the rocky planets. Here's another one. This is Comet 67P. Water came from asteroids. Asteroids are composed of rock, and some of them have water locked into the chemistry of rocks, including rocks from this asteroid right here, which we just recently got samples of this asteroid back on Earth, thanks to the OSIRIS-REx spacecraft. There is absolutely water locked into the chemistry of the rocks of this particular asteroid. And asteroids like these impacted the surfaces of Mercury and Venus and Earth and Mars in our very early solar system. And you can see the evidence of these impacts. Those are craters. And here's Mercury. It's covered in craters. Mercury also contains remnants of ancient volcanoes. But why doesn't Mercury have air if it had the volcanoes releasing the gases and the comet impacts and the asteroid impacts? Why is there no liquid water here? Why is there no air here? Mercury was too small to hold on to its atmosphere and too close to the sun for liquid water to stay for a long time on its surface. The liquid water boiled away and the atmosphere leaked off into space. It just didn't have the gravity to hang on to all of that. We do see evidence for thick ice deposits in some of the deeper craters at Mercury's North Pole. That's where we've got it colored yellow here. But it's only these areas that stay permanently cold. They're permanently shadowed from the sun. They don't get sunlight on the floors of the craters. So you've got some ice that's built up in some of these craters, and where ice can collect and stick around, it stays. But in the rest of the planet, it's way too hot. And so you have no ice or liquid water or anything else or atmosphere on the surface of the planet. Larger planets like Venus and Earth had enough gravity to hang on to their air. Venus is almost the same size as Earth and has almost the same gravity. It also has a molten middle, but it has a roasting surface at close to 900 degrees and an incredibly thick atmosphere. The jury is still out as to whether or not Venus may have had liquid water on its surface early on in the distant Venus past. Maybe it was a little cooler then. We really don't know. We hope to learn more about Venus in the next few years. There may be some spacecraft that might be headed there to study more about this planet. So stay tuned on that, to be determined once we learn more about Venus. Mars is smaller than Venus and Earth. It has less gravity. It has more gravity than Mercury, but it has a very thin atmosphere. Its atmosphere is eroding into space over time. It holds on to just the barest thin atmosphere, and there is no liquid water on its surface currently. There are signs that Mars used to have liquid water on its surface in the past. Here you can see evidence of a dried riverbed on Mars. Hope I didn't just say Mercury, Mars. So we've got what looks very much like a dried riverbed. This mineral right here, this lighter colored stuff, we found minerals on Mars that suggest that water concentrated those minerals to such a high degree that we're finding them in high concentrations in the soil. The mineral found in this particular location shows that this location that you're seeing a picture of right here was likely the site of a hot spring. This is absolutely evidence of liquid water in the distant past on Mars. This is ancient dried mud. Mars was wet 2 to 3 billion years ago, but not anymore. It lost its atmosphere over time. If there was liquid water there, and it bubbled away, it boiled away slowly into space. Jupiter's moon Europa. Probably didn't expect me to talk about some moons, but these are interesting places in our solar system. Jupiter's moon Europa has an icy surface, and under that surface is a saltwater ocean. Same water that comes out of your faucet, same salt that you've got in your cupboard. Saturn's moon Enceladus also appears to have a reservoir of salt water. Worlds like Europa and Enceladus have caused us to start to expand the range of worlds that are at least interesting to think about, that could have conditions that might be favorable to life. Is there an atmosphere here? No. Moving plates? No. But there's a thick layer of ice and water underneath. That means the water is warm enough to be liquid. So an interesting place to think about. It's not just the planets that we have to think about as possible places to try to figure out, could life have existed here in the past? Does it exist there now? Some of these moons, even far from the sun, might be interesting places to, like I said, at least think more about in the future, at least consider. All right. Varied landscapes. This is an interesting one to also consider. We have mountains, we have deserts, we have forests, we have plains, we have tundra, we have an amazing array of life on this planet. Now, the dramatic effects of our planet's moving surface formed different surface habitats in different terrains. You've got some land that's higher and lower. You've got some land that's warmer and colder. All this difference spurred adaptation of life, and this caused immense variation in the types of life that are found here. As life was slowly adapting to different conditions, this helped life to diversify and survive many mass extinction events. And here's a really interesting example, and this was the best map I could find. It's in a not English, it's not an English language version of this map, but this is the Great Rift Valley in Africa. And this is a loosely connected series of valleys and rifts. This Rift Valley system stretches from the Middle East to southeastern Africa, and the rifting has caused the Red Sea. Basically, you've got two areas that have pulled apart. They're pulling slowly apart, and so the land in between would be falling. The land is pulling apart, and then it's come apart far enough up to the north for water to rush in and for the Red Sea to form. This is the Jordan River Valley, and you can see where you've got two areas of these plates. They're pulling apart, and the valley in between is where the river is. And so this area is dramatically pulling apart. You've got lower land down in the middle. You've got land up higher on the edges. Now, this area started off flat in the Great Rift Valley, and it was lifted due to liquid rock rising from below the surface. Over time, this has created a lift and a high valley ringed with tall mountains of volcanoes. In Ethiopia, you can travel from a rainforest to a desert all in the space of 30 miles. And this movement over time of all these landforms pulling apart, some of it falling, some of it rising, has created incredibly diverse landscapes and wildlife, even over short distances. And the movement and variation is going to continue. What's really amazing to think about is that in a few tens of millions of years, this eastern part of Africa will have completely split away from the rest of the continent. This whole area is going to form an island. It's in the process of doing it. If you take a look and see where the water is here, this is where the split is happening. It already split enough to the north. It's continuing to split here along the side of the eastern side of Africa. Eventually, this whole area is going to be an island on the right-hand side of Africa. It's going to look completely different. And just like the island of Madagascar, where you've got some very diverse wildlife that you don't really find elsewhere, the same thing over time is going to happen to the wildlife that is on this particular large island. But again, a few tens of millions of years, we got some time. But really neat to see this happening. You can kind of see this rift happening slowly right before your eyes. One of the reasons we may be here is our moon. Most of the moons in our solar system are only about 1/100th the size of their planet. And our moon is about 1/4 the diameter of our planet. There are very few moons that have this sort of size scale as it does to our own planet. Our moon is big enough and close enough that it actually stabilizes the rotation of Earth. If we did not have a big moon, we would not have tides. We would not have all the life forms that depend on the tides. We would have regular wind speeds on this planet that would reach several hundred miles per hour. Normal wind speed. Earth would rotate faster than it does now. The pull of the moon's gravity on the Earth helped slow the young Earth's rotation rate. Earth used to spin faster. Now we have a roughly 24-hour day currently, and Earth is slowing down over time. And the moon's gravity pulling on the Earth is causing that to happen. The counterpoint to that is the moon is slowly moving away from us. We will never lose the moon completely, and then eventually the Earth will slow down enough so that the same side of Earth will face the same side of the moon. The same side of the moon currently always faces the Earth, but eventually our Earth will slow down its rotation where the same side will always face the moon, which means part of our Earth will always see the moon. Another part of the other side of our Earth will never see the moon, which is kind of mind blowing to think about. But we have this relationship so that if we did not have our moon, we would spin a lot faster. Our wind speeds would be a lot more. Another thing that our moon does is our Earth is tilted with respect to the sun, and this tilt does change over time. And the changes in our tilt, they change a little bit, a couple of degrees over the course of 41,000 years. And it's due to the gravitational effects of planets like Jupiter and Saturn. This little tiny 2-degree wobble, it can shift our climate from warm to icy over the course of 41,000 years. What would this wobble be without the moon? At least 5 degrees, and maybe of tilt change, and maybe much more than that. The wobble with the moon, about 2 degrees. And so the fact that we have a large moon helps to keep these tilt changes more stable. By the way, in case you're wondering, um, what is more extreme, what is less extreme for tilt? More extreme is more tilted, less extreme is less tilted. The less tilted we are, the less extreme our temperatures and all that. So what are we headed toward right now? Less tilted. We are headed toward less extreme in terms of overall climate here on Earth. So people like to ask the climate change that we're seeing on Earth, is it due to the tilt of our Earth? No, it's not. So if anything, we should be experiencing less extreme over time and not more temperature extreme. Okay, so carbon, liquid water, uh, um, moving plates, we've got a large moon. What else? What else do we got here? Well, I'm going to combine these two. We're not too close. We're not too far. We're not too big. We're not too small. We're kind of you could say in a little bit of a Goldilocks situation. Earth orbits in what some people call the Goldilocks zone. We're not too close to the sun, so we're not too hot. We're not too far from the sun, so we're not too cold. And what does this mean? Water is liquid on our surface. Our planet is also not so small that we've lost our atmosphere to space, like Mercury and as Mars is doing now. We're also not too big. What is too big? Jupiter. Large planets are made mostly of gas and liquid, and they have crushing atmospheres and powerful storms. We definitely are not like Jupiter. We are definitely are not like Saturn. These planets are made mostly of liquid with interiors that are just a slushy mix of rock and ice, and just there's nothing here to stand on. These are very inhospitable places. These are not places like our planet. Like I said, on Uranus, there's no hard surface to stand on. On Neptune, there's no hard surface to stand on. So the gas giant planets are definitely not places we would expect to find life at all. So you can be too big. You definitely can be too small. You can be too close, you can be too far. We're in just the right place. Now, thinking about the other main reason why we're here, we have a star, our sun, but it's very stable and it's been around a long time. Our sun makes life on Earth possible. Now, when I mentioned it's very stable, yeah, it spits off flares every now and then, little bits of energy release that you might see in like this little video clip right here. It spits off larger releases of energy and material. But all in all, our sun is remarkably stable in terms of the amount of energy it emits. This doesn't happen very often. You don't see a large release of radiation from the sun all that often. That's what you're seeing here. All that white stuff is radiation overwhelming the detectors from the spacecraft that took these images. This doesn't happen much, and that's a good thing. Our sun is a long-lasting star, and by long-lasting, I mean billions of years. The brightest star in this picture right here is a very hot, large blue star. This star is only about 3 million years old, million with an M, and it likely will only last a few million or so more years. Hot stars go through their fuel very, very quickly, and large stars like this one will eventually explode. If planets form around stars like these, they're just not around long enough for life to take hold. At the other extreme are stars that are cooler and smaller than our sun. These stars go through their fuel very slowly and last a long time. It sounds like it would be a good thing, but the problem with these stars is they're so cool and so small, you have to have a planet that orbits so close to get any heat. More than likely, the gravity of the star is going to tug on the planet so much that the same side of the planet is going to always face the same side of face the star. One side would be in perpetual daylight, the other side in perpetual nighttime. This could create some really drastic extremes on this planet. And sometimes these little tiny stars give off huge flares, often doubling their brightness in minutes. Imagine if you were outside one day and all of a sudden the sun gets twice as bright as it is now. That doesn't happen here. It's impossible to fathom that. But these small red stars go through this often. These energy bursts would irradiate the planet. And so these would not be hospitable places for life. It doesn't mean life couldn't exist there. They would just be in pretty harsh conditions. We have a magnetic field. Have you ever done the experiment where you put a bar magnet on a table, put a piece of paper over it, and sprinkle iron filings on that? You might have done that as a little science experiment, maybe in elementary school or grade school. Well, imagine our whole planet is a giant bar magnet. Studies of ancient lava rocks in Australia and other rocks in South Africa have concluded that our planet has had an internal magnetic field for at least 3.5 billion years. That's a really long time. And if you want to see a visual reminder of our magnetic field, take a look at an aurora. And yes, this is me. And this is the Northern Lights in Northern Canada, taken 5 or 6 years ago. Our magnetic field deflects damaging radiation from the sun and these outbursts from the sun. And so we have a magnetic field that causes that energy and that material to flow away from our planet. But the interaction of that material from the sun with our magnetic field eventually causes some of our air to glow. And this is what the auroras are. And it's a really good thing that we have a magnetic field. Let's take a look at a simulation of what one of these outbursts looks like when it slams into our magnetic field. Imagine the radiation from the sun, all that material and energy just hitting our planet directly. But no, our magnetic field bends it around. Let's take another look. Look at that. That's a really good thing that we have a magnetic field. It deflects all that excess energy and radiation from the sun. Does Mars have a magnetic field? It does not. Mercury? No. There's no protection from blasts like this. This is an interesting one to think about because we're not sure if having a Jupiter is a necessary case for life being on Earth, but we have giant planets that protect us from afar. In the early solar system, Jupiter's strong gravity would deflect asteroids, and a bunch of them got deflected toward our planet. This may have brought those water-containing asteroids to our planet. Today, Jupiter thins out the asteroid belt. It thins it out, but also keeps the asteroids contained pretty much in between Mars and Jupiter. All right. So Jupiter is kind of there shepherding a vast amount of the asteroids, and it tends to deflect stuff away from us. We have this protection that, well, sometimes Jupiter's strong gravity can cause stuff to hit it and not us. This protects Earth from overly frequent collisions that might trigger extinctions. But what's an example of one of these frequent collisions? Well, in 1994, this comet right here, called Comet Shoemaker-Levy 9, it was one comet. Jupiter's gravity first pulled it into orbit around Jupiter and then pulled it apart into about 30 different pieces. And each one of these pieces slammed into Jupiter. And you can see one of those collisions right here. That's the brightening right here. By the way, the other dot is Jupiter's moon, Io. So that is one of those bits slamming into Jupiter. All right, so this was in 1994. What was the aftermath? See all these dark splotches? Each one of those is due to a piece of the comet hitting Jupiter's atmosphere and exploding. Can you imagine if that comet had hit Earth 30 different pieces? It's amazing. The rate of comets hitting Jupiter is thought to be up to 8,000 times higher than comets hitting Earth. Some astronomers have thought that without Jupiter to mop up these potential impactors, extinctions on Earth may have happened a lot more often, and complex life forms may not have had a chance to develop. It's an intriguing possibility. More study needs to be done on this. We don't know for certain if we need something like a big planet, Jupiter, to protect us, but definitely something that folks want to look into. And then finally, we live in an uncrowded corner of an interesting galaxy called the Milky Way. All right. So, what do I mean by uncrowded? Well, to sustain life, planets and solar systems can't be crowded in groups of stars that would jostle them around too much. What you're looking at is a cluster of stars that contains about 100,000 stars. So you're not even seeing all of them in this particular picture. But in this whole entire cluster right here contains about 100,000 stars. Now, in the same volume of space in our neighborhood in the Milky Way galaxy, how many stars are there? So the volume of space taken up by this cluster right here, how many stars do we find in our neighborhood? And the answer is 133. So would you rather live in a neighborhood that had over 100,000 stars or a neighborhood that has 133 stars in the same volume of space? This means there are relatively few stars near our sun. We have relatively few risks to Earth from gravitational tugs from those stars or bursts of radiation from those stars. So being in an uncrowded corner of the Milky Way galaxy is actually a very good thing. And I just realized I forgot to do a screenshot of this particular page. We're going to go to this page when I stop sharing my screen. We'll go to this page and see what the current count is for the number of planets found around other stars. How many have we found with life on them? None so far. How many have we found that are actually Earth-like? None so far. We found some that are Earth-sized, but we need to know about all this stuff. Do any of them have carbon? Do they have an ozone layer? Is their surface moving? Do they have liquid water? Do they have lots of different landscapes? A large moon? Are they not too big, not too small, oh, not too close, not too far? Is their star a stable, long-lasting star? Does it have a magnetic field? Does it have a big planet nearby? And is it in an uncrowded area of the Milky Way galaxy? All of this would start to tell us if something is Earth-like. So I'm going to stop sharing for a second and let me real quick go to that page. I'm going to share my screen. Hang on. I want to see what the current count is for planets around other stars. When I did that screenshot a little over a year ago, it was 5,035. And the current number about a year later, 5,528 planets found around other stars. And how many of them are like our planet? 0 so far. Hope this gave you some interesting food for thought. How amazing life on this planet is. And do we absolutely need all these 12 things to get life elsewhere? Maybe not. Do we need exactly the same 12 things? Maybe not. It all depends on what the conditions are like in those other places. So I would love to know, do you have questions? If so, throw them in the chat, throw them in the Q&A. Debbie sent me a great comment. Thank you, Debbie. She said, thank you for an informative talk. Thank you. I'm gonna take a quick drink of water. Okay. Questions either in the Q&A or the chat. I'll find them. And I
Yeah,
know that,
everybody give questions. I have a question for
yes,
you.
please.
Okay, so I always wonder about these trips to Mars and these billionaire ideas about like, let's go to Mars. But if you have all of these things that are necessary for life on Earth and we are such a Goldilocks planet, why would you even attempt to try and like terraform another planet that isn't in that zone? I don't get it.
You're absolutely right. People ask about terraforming all the time. They want to go, but we could just terraform Mars. First off, what terraforming means, terra means earth, form means change the conditions on at that place to make it more Earth-like, if you could. First off, it would take an extraordinarily long time. It would not be something that you could do over the course of a year or 2 or 10 or 100 or 1,000. It would take a very long time to be able to do that. And you'd be starting a process, which first off, you wouldn't even know for certain if it's ever really going to take, right? I mentioned, oh, sure, you could do something to create more atmosphere. Well, Mars doesn't have a lot of gravity. Its atmosphere is going to slowly leak off into space. So you would have to keep replenishing that atmosphere slowly in order to keep it. You also don't have an ozone layer. Would you make an ozone layer? Well, you're still going to have to protect all your buildings and your and everything from all that excess radiation. Yeah, probably. Why would you do that elsewhere? It, it's something that I like to talk about in my climate change, science of climate change talk, which is there really isn't a planet B. This is the planet that our life is suited for. We can we can build habitats in other places. We can um, protect ourselves and all that, but we're not anywhere near getting 8 billion people to live on the moon or 5 people to live on Mars. So yeah, it really puts it, at least for me, it puts it into perspective as to how special Earth is. Now, I'm not saying Earth doesn't exist elsewhere. There very well could be another one. All we need is one other one to show us the array of diversity of places where life could exist. We just need to find one. Where are they? So okay. A and J, I think it says A and J. Do you have any additional information about the potential Venus missions? I'm a much bigger Venus fan than I am of Mars. You and lots of other scientists out there as well. So NASA initially had a couple of Venus missions on the books. One of them definitely got delayed. There was a problem with a different mission, and in order to get that one back on track, they had to delay one of the Venus missions. So I think one of them may have gotten canceled and one of them got delayed. So it's okay. The European Space Agency is going to send a Venus mission also. So there's at least another one, if not two, missions that are going to go explore Venus, but it wouldn't be until I think it's the late 2020s, early 2030s, somewhere around there. You're right. Venus has gotten the short shrift here. Everybody's paying so much attention to Mars. Whereas if we found a Venus around another star, we go, it's Earth-like, right? It's Earth-sized, it's Earth gravity, it's got an atmosphere, it's got volcanoes, it's got all sorts of stuff. Got 900-degree temperatures, but can't have everything. But yeah, it's a fascinating planet to think about, and we definitely need to learn more about it. So, John asked a great question. How do the criteria fit into the Drake equation? So for everyone's reminder, the Drake equation was I guess you could say a theoretical equation that was put together by an astronomer by the name of Frank Drake back in the 60s, I think. And it was really just he designed it as just a discussion point. He was going to be going to a conference and they wanted something to talk about, and so he said, "Okay, um, let me bring up the Drake equation because I'm going to forget all the elements." Hang on, let me grab it, and this is why sometimes I love doing these via Zoom because here we go, because I can actually share my screen and show you stuff on the fly. So hang on, let me grab this. Okay, so give me a sec. Okay, so over here on the right-hand part of the screen is the Drake equation. And N is the number of civilizations with which humans could communicate. So advanced civilizations similar in technological advancement as humanity, right? So R is the rate that stars form. We know what that is. FP, the fraction of stars that have planets. We're definitely getting better at that one. We have a pretty good idea of what that is. NE, the number of planets that could support life per star with planets. We're still guessing at that one because we don't have a number for that, not yet. We need to find at least one other place that has life in order to even start to get a sense of what that number is. The fraction of life-supporting planets that actually develop life, no idea. The fraction of planets with life where life develops intelligence, no idea. Fraction of intelligent civilizations that develop communication, no idea. The mean length of time that civilizations can communicate, no idea. So here we've got a giant problem with the Drake equation, which is there are several of these elements to it that are pure guesswork. We have no way for sure of knowing with the information that we've got now about life elsewhere, no way of knowing what several of these numbers are. They're just pure guesses. Now, where the criteria that I talked about, where that all plays a part, is kind of the NE, the mean number of planets that could support life per star with planets. So what are we getting into in terms of the conditions for life on that planet? Which of these do you need? What subset of those 12 do you absolutely need for life to be on that planet? All right. So that's everything I just talked about is pretty much in that one number right there. What makes it so that planets could host life? That's really all that's about. And the rest of those after that, pure guesswork. You could argue for weeks on one side or the other versus for the number for this one and the number for that one. What Frank Drake never meant was for this to be a hard and fast equation either. You could totally move things around and discuss and all that. And there's no way to really assign a number to a true number to an answer to the Drake equation because so many of those elements to it, those parts of it, we don't have numbers for at all. So, but he definitely started a discussion that has gone on for decades as to what it all means. And could you actually add to that? Absolutely. Could you refine all that? Sure. Um, and then how much of it are you guessing at? Most of it, about half of it at least. And R.I.P. Frank Drake. He passed away not too long ago, so his legacy lives on for sure. And he's definitely known more for the Drake equation. Um, he's done a lot more than just that equation. So
All right. Well, if anybody else has any questions, I saw a comment from Robert come through. Thank you, Robert.
thank
That's so
you.
kind of you. Yeah, I have another question.
Sure.
So, you know, the Voyager record,
Yes.
the item that we sent out into space, you were talking about like we have to be intelligent enough to communicate with something else, and something else might see that record and be able to decipher, oh, there's intelligent life in the universe. Um, it's just floating out there. What's it doing out there? It's just floating forever.
Yeah. Basically, the Voyagers are going in certain directions. In terms of the direction that our solar system travels through the Milky Way galaxy, one of them, they're both kind of going in ahead of us. One up a little higher, one up a little low, or one down a little lower. So they're kind of doing that. And um, basically, they're just going to keep going until they run into something. And the chances of them running into anything is pretty small. Now, people have said, oh my God, we've just sent a signpost out there, two of them, that said, Earth is here. Here we are. Here's our map. Here's where you can find us. Don't worry about that. It does not matter. We have been announcing our existence for decades before we ever sent the Voyagers out there. For all of our electromagnetic radiation that we sent out, our TV signals, our radio signals, everything, all of our technological advancement announced our presence well before the Voyagers ever went out there. Yeah, yeah, it's John says gangbusters is going out in all directions. I wonder if you meant Ghostbusters. Yeah, it's going out in all directions. Absolutely. Yeah, every terrible movie we've ever created and broadcast is now out there. So any civilization within probably 80 to 90 light years of our sun, they know we're here. So it does not matter that the golden record has the or the pioneer plaque with the exact location of our planet if you can decipher all the information on there. Yeah, it's okay. It's fun to think about. And and a whole Star Trek movie. Star Trek One was based on finding the Voyager spacecraft, Voyager 6, but there is no Voyager 6. Not yet anyway. So, all
All right.
right.
Well, I love that Star Trek plug.
Yep, and I'll bet you the library has it on DVD, and if not, you can get it. So if you have not seen the first Star Trek movie, it's not the greatest one, but it definitely was something that is near and dear to my heart because it was one of the first sci-fi movies I ever saw. Saw Star Wars and the first Star Trek, and that, among other things, got me interested in astronomy as well as Carl Sagan and cosmos, and he does talk about the Drake equation and all of that. So it's a fascinating tie-in with sci-fi and sci reality. So
Yeah. All right. Well, I love it. Thanks everybody for joining us tonight. And thank you again, Michelle. Please remember that she's going to be back with us January 22nd for constellations. And then we're going to talk about Artemis and returning to the moon May 20th.
yep,
All right.
excellent.
Well, have a good night, everyone. Thank you all for joining us. Oh, we have a
Oh,
final question. Did you
oh
want to answer?
yes. Are any planetary moons candidates for life? Yes. The two that I mentioned, Enceladus and Europa. So Europa, a moon of Jupiter, Enceladus, a moon of Saturn. And the candidates for life are basically based on the liquid water underneath the icy crust. Um, uh, the and there could be some of the elements there that life may be able to live off of. Now, are there magnetic fields? No. Moving land crust? No. Various other things that we do have that those planets don't have. However, like I mentioned, just because we have those 12 things doesn't mean you might not, it doesn't mean you need all 12 things. So wouldn't it be interesting to dig down below the ice and turn on a camera and see if there's anything staring back at you? Um, I don't know if that'll happen anytime soon, but it's a fascinating thing to think about. But yes, we absolutely have to think about some of these larger moons because a couple of them are reservoirs of liquid water. Lots of moons have ice, water ice, but a couple of them have liquid water, and we have to think about those as candidates, at least for more study. They may not have life, but they are at least broadening out our expectations. We don't just look at how close or far you are from the sun. That alone is not the only criterion. So yes, we live in the Goldilocks zone, but that's not the only thing that is important for life to potentially develop on a world. So yeah, those two, definitely read up on those two.
All
So,
right.
all
Okay.
right.
Well, that's so wonderful. Thank you so much again. And we'll see you back again in January.
I'll see you in January. Thanks, guys.
Okay. Bye.
Bye.